In section 3.8, we are going to find some general rules for derivatives of logs and exponential functions, and that will make it nice. I'll be able to come up with these general rules, and I won't have to use the limit definition for the derivative, which is cumbersome and tedious. So if I can come up with these general rules, prove them, then I can use them for general problems, and then I'll practice with these general problems. In the left corner up here, we see just some inverse properties. They're there just to remind you that they exist and what they are. We're going to be using this one right here in our proof for the derivative of the natural log of x. Let us begin with y equals natural log of x. It's natural log of x, and know that we want to come up with y prime. Alright. We don't know any general rules right now for natural log of x, but we do know one for e to the x. We came up with it a while back, and I'm just going to set it up here at the top. And I went ahead and wrote it for e to the u instead of just plain e to the x, and it's just a combination of e to the x and the chain rule. So it's e raised to some function of x. I can write y equals natural log of x using that inverse property 2 as x equals e to the y. And we learned implicit differentiation, I believe, in the previous section. So I'm going to take the derivative of both sides. Taking the derivative of x, that would be a 1, equals the derivative of e to some function of x is e to the y prime. This yields y prime equals 1 over e to the y. Y happens to be the natural log of x, so I'll rewrite that. 1 over e to the natural log of x. This simplifies using that inverse property 1. It's 1 over x. If I wish to take the derivative of the natural log of x, the answer to that will be 1 over x. Remembering that the natural log, I can't take the natural log of 0 or negative numbers, so it has some domain restrictions to it. That's why we see a restriction here for the answer to the derivative of the natural log of x. However, if we go ahead and say that we're taking the derivative of the natural log of the absolute value of x, meaning that I eliminate those negative answers, then I can say that it is 1 over x for all x, except of course that case where x is 0. This is an extension of the natural log of x using the chain rule. That's where this came from. You might rewrite that as saying y equals the natural log of some u, where u is a function of x, and using the chain rule, it might look a little prettier if I were to say that y prime then equals u prime over u. Just not quite as messy with all of the notation in here. It's kind of the way I like to look at it. So I wrote the general rule up here at the top. I like the general rule the best. This involves the chain rule. So the natural log of some function of x is that derivative of that u divided by the function. So let's play. Y prime equals, note here that u equals 4x. So I have the natural log of u. U prime would be 4 over u is 4x. Y prime in this case is 1 over x. Perfect. The next one, Involves the product rule. Got x times the natural log of x. And using the product rule, I'll take the derivative of the first one, the derivative of x is 1, leave the second one alone, plus, leave the first one alone, take the derivative of the second. The derivative of natural log of x is 1 over x, making this pretty. So natural log of x plus the x's here cancel, 1. Next, I have y prime equals, this is a natural log of some function, so I will have secant x. The derivative of secant x is secant x tangent x. My secant x cancel. The derivative is tangent x. Next one, this is a bit of a mess. It involves the quotient rule, and then my numerator has this natural log of some function in it. Okay, quotient rule. It's low times the derivative of the high, so low is x squared times the derivative of the high. The derivative of the natural log of x squared is u prime, which is 2x, over that u, which is x squared, minus, so it's low d high minus high, natural log of x squared, times the derivative of the low, which is 2x, all over the low part squared, so that would be x to the 4th. Really messy here. Y prime is, oh well, these x squareds cancel, and that's nice. Oh, and then I've got 2x minus 2x natural log of x squared. Alright, so let's see. Oh, and I didn't take, yep. Yeah, I could have factored out that 2x there. So let's go ahead and look at that. Oh, you know, I could bring this 2 down if I wanted to using the properties of logs and make that, I'll just factor out the x and then do 2 minus 4 natural log of x. That looks a little prettier. Guess I could have done that, made that 2 natural log of x at the very beginning too, couldn't I? Either way, I'm still going to get the same answer. Y prime equals, and then I've got 2 minus 4 natural log of x over x cubed. Okay. You could factor that 2 out, won't do anything, but if you like it that way, you could write it that way too. To come up with the general rule for the derivative of some constant b raised to the x, I'll be using inverse properties. So let's look at b to the x, and I know from the inverse properties that b to the x can be written as e to the x natural log of b, where the natural log of b is just some constant. So it's just like a number times x. I've already completed a proof for this bad boy, so I'm just going to use that thing. So if y equals b to the x, then I can say that y prime is, and I'll be using the fact that b to the x is equal to e to the x times some constant. This tells me write down your e to the u, so that is e to the x natural log of b times the derivative of my u. Now my u in this case happens to be this whole thing, and this is a constant times x, and a constant times x, the derivative of that is just that constant, natural log of b. And rewriting y prime equals, this is b to the x times natural log of b, which is what they got here. So we've now proven the derivative of b to the x. Now let's play. My b in this case is 3. So f prime of x is my rule, general rule is b to the x, so that would be 3 to the x times the natural log of my base, natural log of 3. All done. That's about as simple as it'll get. So I can't manipulate it and make it look any prettier. G of t. I have a constant. Here's my b to the x, so it's some constant times b to the x. My derivative says, and I know that with the constant multiplier, just leave that there. I'll write this down as, and this involves the chain rule because this isn't just a plain x, this would be a u. So my u in this case is that t to the 12th, t over 12, excuse me. And what I will do is I'll take the derivative of the outside. The derivative of the outside is 2 to some power, so that's 2 to the t over 12 times the derivative of the outside. I still need that natural log of 2, which is my base, times the derivative of the inside. The derivative of the inside, t over 12, is the same as like 1/12 times t, so that's just a constant, times that t, which would then be 1/12. Now this will simplify a little bit. I know that 12 goes into 108 9 times. I think that's about all it'll do. So I got 9 natural log of 2 times 2 t over 12. And I believe that would be it for that one. It's about as pretty as it'll get. Word problem, let's see. They give me the function. A is the age of the mother and P is the incidence number. Okay. What is the age? So they're looking for A, and the incidence number is 0.01. All right. So that is 1 in 100. So if I were to really look at it, it's going to be somewhere in between 40 and 42, closer to 40, I'd say. All right, let's see what the real number is. A, there, 0.01 equals 1 over 1613000 times 1.2733 raised to the a, and a is what I'm looking for. This is just a straight algebra problem. Move this sucker to the other side, take the natural log of both sides to get the a out of that exponent, and then I will just crunch the numbers. Alright, just multiply both sides by that. I'm going to take the natural log of both sides. This is just going to be some number. Using my log properties, I can bring this a out front. Natural log 16130 equals a natural log 1.2733. Divide both sides by this constant, natural log 1.2733, and I'll have what a is, and then I'll crunch the number in my calculator. I get 40.1, which is about 40 years old, which I knew that already because I knew that was pretty darn close to that 40 right there. B part, compute the derivative, P prime of A. I see that I have a constant multiplier, so I'll just write that down. One more 0 times the derivative of some b to the x. The derivative of b to the x is b to the x, which is 1.2733a, times the natural log of my base, which is natural log 1.2733. 0.2733. Making it a little prettier, I guess I can put the natural log on top over here and just rewrite. Okay, I've written it a little more neatly. You could go ahead and crunch those numbers and get one solid number if you'd like. This is also fine. The C part, I need to find P prime of 35, which just means I'm just going to put a 35 in here for A and crunch those values. And then I need to find P prime of 46. I'm going to just plug that in and crunch those values, and then I'll be right back. After plugging those numbers in the calculator, I get that the rate of change of the incidence number is 0.0007 if you're at age 35. However, that incident rate goes up dramatically when a woman hits 46 to 0.01. And when you're talking about their derivative and they ask you to include the word rate. It's the rate of change of incidence over, with respect to, in this case, age. So it's the rate of change of the incidence number with respect to age. So be sure to include that word rate anytime you're asked to interpret. So we have a new theorem, which is a theorem that we've already been looking at, but using exponentials we can expand that so that the derivative of x raised to some constant power, as long as it is a real number, which we've done it for integers, and then we expanded that even further for rational numbers, meaning fractions, and now we expand it once again, x raised to any real number. We will just drop the power drop rule. We drop the power and subtract off 1. And this second part just extends it using the chain rule. So we're going to play these games and we're going to use our rules and see if we can come up with the derivative for the following functions. I just copied and pasted the general rule for the derivative of b raised to some x and b raised to some function of x, and that's what u is. U is just some function of x, and it's an expansion of this first rule using the chain rule. So you'll notice that it's the natural log of b times b to the u times the derivative of what's on the inside, and it just is using that inside-outside function. Alright, so let's play. Y prime equals, what do we have? Do I have, as I have here, an x in the exponent, or do I have a real number in the exponent with x as my base? This will use the general power rule because x is at the base. I drop my pi, and it will be x to the pi minus 1. All done. This next one, I won't use the general power rule because x is in the exponent. Notice the difference between a and b. X is in the exponent here. This means I would need to use, this one would be the simplest, so I'm going to use this first one here. Y prime, just the general rule for b to the x. And my base in this case happens to be pi. So it will be my b to the x, which is pi to the x, times the natural log of whatever my base is, and my base happens to be pi. Notice that these two answers are quite different. One has the pi in the base and one has the pi in the exponent. Make sure that you note the difference there. Now this next one is some sort of function raised to the power e. E is just a number, it is just a constant. So what I'll be using is this general power rule because I have x raised to some p. I actually have a u raised to some p like they have here. So y prime in this case, u raised to some p would be drop your power, And I'm going to be using the chain rule basically, or you can use this mess here, which is an expansion using the chain rule. I'll bring my e down front, x squared, leave the inside alone, e minus 1 times the derivative of the inside. The derivative of the inside would then be 2x, making it look a little bit prettier but not much. 2e x squared plus 4 raised to the e minus 1. Alright, this next one's going to be a booger. I went ahead and got these two rules here that I'm going to need. One is from the inverse property of logs, and the other is the rule for the derivative of e to the u. Notice here that I have x raised to some function of x. I have rules for x raised to constant powers. I don't have rules for x raised to some function. So I can't use any of my general power rules basically, but I can rewrite this using this inverse rule. I'm going to rewrite this as equals e to the sine x natural log of x, because I do have general rules for e raised to a u. I've already worked that out. So f prime of x equals e to the u, which my u is this sine x natural log of x. So e to the sine x natural log of x times the derivative of my u, and there's my u. I will need to use the product rule for that, so I'm going to take the derivative of the first, cosine x, leave the second one alone, add to that, leave the first one alone, and take the derivative of the second. Derivative of natural log of x is 1 over x, so I'm just going to write it like this. And this will equal this guy right here, using the inverse properties, is just my x sine x, and this guy here doesn't really simplify much at all, so I'm just going to leave it alone. It's just ugly. The second part wants me to just plug in pi over 2. Okay, so f prime of pi over 2. So wherever there's an x, I'm going to write a pi over 2. Pi over 2 raised to the sine pi over 2 times the cosine pi over 2 times the natural log of pi over 2 plus sine of pi over 2 over pi over 2. The sine of pi over 2 is 1. So pi over 2 raised to the first is pi over 2. My favorite, cosine of pi over 2, that's a 0. So it doesn't even matter what that dumb thing is. That sucker's gone. The sine of pi over 2 is a 1. 1 divided by pi over 2 becomes 2 over pi. And this silly thing is a 1. Now once again, I don't have a rule for x raised to some function of x. I'm going to pull this little trick that I used before, and I'm going to say that f of x equals, and then what I would write is ex to the natural log of x. So in order to find a horizontal tangent line, I have to know the slope formula. So here's my slope formula. That's the derivative. And I now have some e to the u, so I'm going to use this bad boy again. So that'd be e to the u, e to the x, natural log of x, times the derivative of my u, product rule. Derivative of the first is 1, leave the second one alone, plus leave the first one alone over the derivative of the second, well, times the derivative of the second, but that's 1 over x. So f prime of x equals, this sucker is x to the x, and then I got natural log of x plus 1. So where are their horizontal tangent lines? This thing is already factored for me. So if either one of these two is 0, the whole thing is 0. X to the x can't be 0. If you graph that, look at it, you'll see that x to the x is positive. So the only place that that could happen is the natural log of x plus 1 equal to 0. Solving this using my algebra skills, natural log of x equal -1. In order to get that x out of that natural log, I'll kind of e both sides, and I will get x equals 1 over e. So when x is 1 over e, that would be where I would have a horizontal tangent line. And because of the fact that I can take the derivative of the natural log of x, and the natural log of x can then be transformed into log at any base using that change of base rule, those general rules apply for log of any base. So we're just going to play the game here, knowing that that's how that proof would be completed. This is log base 5 of some function of x, so we'll say u, and we're going to be using the chain rule. The chain rule says take the derivative of the outside. The derivative of log base 5 is 1 over whatever that is on the inside. In this case it would be 2x plus 1 times the natural log of whatever my base is, so that would be the natural log of 5. Using the chain rule, I would then multiply by the derivative of the inside, which would then be a 2. Cleaning this up, f prime of x equals 2 over natural log of 5 times 2x plus 1. Not very pretty, but it is what it is. Next I need t prime of n. I see the product rule here. Take the derivative of the first, that would be a 1, log base 2 of n, plus n times the derivative of log base 2 of n, so that tells me I'm going to say that is 1 over n times the natural log of my base, which would then be 2. Tink, tink. This thing simplifies to log base 2 of n plus 1 over the natural log of 2. Notice how messy this thing is. Oh my goodness, if I were to really work this one as is, which I could, I would have product rule, quotient rule, and chain rules all in here. Logarithmic differentiation is a technique that makes all of this somewhat simpler once you figure out how it works. So what I'm going to do, this is just another tool to put in your toolbox. I'm going to take the natural log of both sides, and then I can simplify this thing a whole bunch. So the natural log of all of that stuff. The next thing I'm going to do is use my log properties to make this just sums without the exponents and without all the product and quotient stuff going on. Next I want to take the derivative of both sides with respect to x. And while the left hand side might look a little strange, what it really is I'm taking the derivative of the natural log of f of x. Think about using the chain rule. The chain rule would tell me take the derivative of the outside. The derivative of the natural log is 1 over f of x multiplied by the derivative of the inside. The derivative of the inside would be f prime of x. Next I'm going to take the derivative of each one of these independently because they're sums. So the derivative of this first term is 4 over the u, because that's the derivative of log, multiplied by the derivative of the inside, so that would be 3x squared, plus I would have 1/2, so 1/2 times the derivative, times just the u, 3x minus 1 times the derivative of what's on the inside, that would be a 3, minus, doing this thing again, the 1 over x times what the derivative of what's on top, that would be 2x. So now I'm going to multiply both sides by f of x, because I like to know what f prime of x is. And I'm just going to write all of that stuff down and simplify a little bit. Alright, that's all I've done, is I just simplified the stuff. All I could do was something with the first term, and then just wrote down my f of x, and that thing is really messy. I know it is. It's ugly. Sorry. But that's way better than trying to use the chain rule and the quotient rule. But I could. You'll still end up with something of this form. And that's all of section 3.8. And if you have any questions, you know where to find me. Email or the Collaborate.